Hi, my name is Junfeng. It's my great pleasure to introduce efficient wideband spectrum sensing using MEMS acoustic resonators. This work is done in collaboration with Jitian, Ruochen, Hyungju, Jin, Songbin, and Haitham. The wireless spectrum has changed significantly in the past decade. For example, in 2020 alone, the Federal Communications Committee (FCC) has authorized full commercial deployment in the 3.5 GHz CBRS band. It also released 1.2 GHz unlicensed spectrum in 6 GHz, which will be used for Wi-Fi 6E. Moreover, unlicensed wireless operations in TV white spaces has also been expanded. It's worth noting that all these frequency bands will be shared between new unlicensed wireless applications and the incumbent licensed users. The goal of sharing the spectrum is to exploit the previously underutilized spectrum to accommodate new wireless services. It will improve the efficiency of spectrum use. The more and more spectrum being repurposed for shared use marks a trend of shifting the spectrum access paradigm from the conventional per-band operation to a dynamic spectrum sharing scheme. However, enabling dynamic spectrum sharing is not easy because it requires unlicensed devices to find and access momentarily idle channels by sensing the wideband spectrum in real time. Unfortunately, this is very challenging for mobile and IoT devices because it requires sampling the signal at a Nyquist sampling rate using high-speed analog to digital converters, ADCs. Such high-speed ADCs are expensive and consume lots of power. To avoid using high-speed ADCs, today's systems adopt frequency sweeping approach. They sequentially scan the spectrum and monitor each narrowband for a short period of time. However, since they cannot continuously sense all bands in real time, they can easily miss highly dynamic and fleeting signals, such as radar waveforms. Another approach is to apply compressive sensing or sparse Fourier transform algorithms. But these algorithms only work when the spectrum is sparsely occupied. This defeats the purpose of efficiently utilizing the spectrum. To come up with a better spectrum sensing strategy for finding vacant wireless channels in a densely occupied spectrum, we learn from one of our daily activities, that is looking for an open parking spot in a crowded parking lot. When looking for a parking spot, we don't have to drive all around the parking lot and examine every single spot carefully. Instead, we can take a glance from the end of the rows. If a car partially appears in a spot, we know the spot is already taken, vice versa. Applying this insight into spectrum sensing, we introduce S-Cube, which stands for Spectrum Sensing Spike Train. The key idea is to sample the spectrum along the frequency axis, and we monitor only the sampled small fractional bandwidth in every band. Then, we use these sampled frequencies to infer the band occupancy. In this way, S-Cube can efficiently monitor the real-time occupancy of multiple frequency bands in a wideband spectrum. It can achieve 8.5 times subsampling below the Nyquist sampling rate, so it can roughly reduce the power consumption by 8.5 times. And most importantly, S-Cube does not assume the spectrum to be sparsely occupied, so it can work in densely occupied spectrum. So the question is, how can we sample the spectrum along the frequency axis? The enabler of frequency domain sampling of a spectrum is a novel RF filter we developed, which we refer to as the spike train filter. We designed this filter to have many narrow, sharp, and periodic passbands across a wideband spectrum. It can pass a small fractional bandwidth in every band and filter out all the remaining frequencies. As a result, the output spectrum is sampled at the periodic filter passbands, and it becomes very sparse, so we can sample the signal below the Nyquist sampling rate and still be able to recover the channel occupancies. Our spike train filter builds on recent advances in MEMS filter technologies. MEMS stands for micro electromechanical systems. These devices can convert RF signals into acoustic waves for processing, and then convert acoustic waves back to RF signals. However, not all RF signals can be efficiently converted. The signal frequency has to match the resonance frequencies of the MEMS resonator, which is determined by the geometry of the piezoelectric material. In this work, we use a spike train filter with 19 spikes, and the spacing between spikes is 22 MHz. So it covers a 480 MHz frequency range. Translating S-Cube into a practical system requires us to solve two key challenges. First, we need to design an algorithm that can reconstruct the spectrum occupancy from the sub-Nyquist sampled signals. Sampling below the Nyquist rate results in aliasing in the frequency domain. That is, multiple frequencies in the wideband spectrum map to the same frequency. For example, if we subsample the spike train XF by a factor of 2, then every two frequency will map to the same bin in the digitized spectrum YF. However, ideally, we want at most one spike to map to a beam, because if two spikes collide in the same beam, we will not be able to distinguish and estimate them. To avoid frequency collisions, we leverage the uniquely structured sparsity pattern created by our spike train filter. We choose the subsampling factor to be co-prime to the number of spikes, and we prove in the paper that sampling rate selected in this manner guarantees no two spikes will collide. The second challenge S-Cube has to resolve is the non-ideal spike train filters in practice. The spikes in a practical spike train filter have some width, and they are not perfectly equally spaced. As a result, it's very likely that no sampling rates can perfectly avoid all possible collisions. To resolve the remaining frequency collisions, we leverage a second sampling rate because it provides us with a different set of aliasing frequencies for the spikes. And the two different sampling rates will exhibit frequency collisions between different spikes. We select the second sampling rate in a way that any two spikes collide at the first sampling rate do not collide again. And we will only classify a spike as occupied if it's non-empty at both sampling rates. We built a prototype S-Cube spectrum sensor and evaluated its performance through controlled experiments in an indoor spectrum sensing testbed. This testbed consists of 19 USRP software-defined radios. We use it to cover a 418 MHz spectrum with various occupancies, and we use S-Cube to detect the spectrum occupancy. Here, we show some results of S-Cube. First, we show the occupancy detection accuracy in the form of false positive rate and false negative rate, as we change the spectrum occupancy all the way from 10% to 90%. As you can see, S-cube achieves very low error rate, even in densely occupied spectrum. Besides, we also compare S-cube with state-of-the-art wire work, including sparse Fourier transform-based big band and deep big band, as well as frequency sweeping-based sweep sense. This table shows the sum of error rates. As you can see, S-cube outperformed wire work, especially in densely occupied spectrum. In addition to detecting the channel occupancies, S-cube can be extended to sense all frequencies in the spectrum and capture the wideband power spectral density. This can be done by combining frequency sampling and frequency sweeping, because we only have to sweep the local oscillator frequency over the gap between two spikes. The sweeping time is much shorter. Using this extended S-cube prototype, we captured the power spectral densities created by our testbed. We also measured ambient transmissions, both outdoors and indoors. We use a spectrum analyzer to collect the ground truth. As you can see, the power spectral density captured by S-cube closely matched the ground truth from the spectrum analyzer. To summarize, we present S-cube, a new, efficient, real-time, and wideband spectrum sensing mechanism that can work in densely occupied spectrum. S-cube leverages a novel RF MEMS filter to enable sampling the spectrum in the frequency axis. Besides, S-cube can also be extended to capture the power spectral density. For more technical details and results, as well as other alternative architectures of S-cube, please check out our paper. Thank you very much.